Lewis structures are a convenient way of showing covalent bonds in molecules or ions of the representative elements. Just like ionic bonding, we'll need to take into consideration the octet rule that says atoms will share electrons to attain a noble gas electron configuration. In ionic bonding, they will atoms gain or lose electrons for this stable electron configuration. But in this case, in covalent bonding, the valence electrons are shared. So let's take a look at how we write Lewis structures and some of the notation. So a single line like this represents a single covalent bond. So this is a single bond here, and a single bond would contain 2 electrons. So a single line like that is a single bond, and it contains 2 electrons. These are lone pairs here, just like when we drew the Lewis structures for an atom. I'm going to write this has 2 electrons. Now, we can also have double bonds, and double bonds will be represented by 2 straight lines here. So a double bond represents 2 pairs, it represents 4 electrons. And again, you see in this structure that we have single bonds and lone pairs. And then finally, we can also have a triple bond, which is represented by 3 lines. And each line represents 1 pair of electrons, so a triple bond represents the sharing of 6 electrons. So let's look at how we would draw electron configurations. Some Lewis structures. Lewis structures for many molecules and ions can be written by inspection, and after a lot of practice you may be able to just figure out by looking at it where the bonds and lone pairs would go. But especially when you're beginning the procedure, it's helpful to have an idea or a process to follow. So this is a process that you can follow for writing Lewis structures. We'll look at this process, and then on the next page I'll follow it. So it says draw arrangement of the atoms. This is what they call a skeletal, like a skeleton, a skeletal structure. So we'll decide which atom goes in the middle and which are positioned around it. We know that hydrogen can't go in the middle. Hydrogen can only have 1 pair of electrons. It can only share up to 2 for its configuration because it only has a 1s orbital. All the remaining of them can have up to 8 electrons around them. Then you'll count the total valence electrons that all the atoms bring. It's these valence electrons that contribute to the bonding. And the valence electrons, this number is super, super important. Third, we'll add single covalent bonds just to make everything attached to the central atom. And then fourth, if there's any remaining electrons that we did not use from our total, we'll add those as lone pairs on the outer atoms. If we still have electrons remaining, then we will place them on the central atom. If we don't have any electrons remaining and the central atom does not have an octet, we'll take a lone pair from an outer atom and make it into a multiple bond. It's kind of hard just to read these rules and get a picture of what we're doing, so we'll go ahead and take a look at some examples to show you how we'll do this. So let's start out with a simple example. We have, I don't want to use a red one, let me change to a black marker. Okay, so let's see, we're given the formula CH4. We have to draw the arrangement first. A lot of times I know that if the first element that's written is going to be in the center, unless it's hydrogen. And let me back up a little. Remember, we're thinking about the octet rule. Now, there are elements that don't obey the octet rule. There's ones that can have fewer than 8 electrons around them, and then there's some that can have what we call an expanded octet and more electrons than 8. In this introductory class, we're going to focus on looking at Lewis structures that fit the octet rule, so we can master that octet rule, and then the exceptions don't seem so big. So hydrogen only has a 1s electron. So what we always know about hydrogen is it can only have a single bond. And it can't be in the middle because if I put it in the middle, it's going to have more than 2 electrons around it. Now carbon can have 4 bonds, and it's going to be in the center. A lot of times, like I was mentioning, the first element written is going to be the central atom. So the first step is just to draw what we call a skeletal arrangement. Lewis structures don't show shape, although they can be used to determine the shape, so I just like to draw mine at 90-degree angles. So this is the skeletal structure. This is step 1. The second step is to add up all the valence electrons, so I know I have a carbon and 4 hydrogens. Carbon is in group 4A, and looking at the periodic table, I know that carbon has 4 valence electrons. Hydrogen is in group 1A, and each hydrogen has 1 valence electron, but I have 4 of them, so I have to add all of them in. So my 4 hydrogens bring a total of 4 electrons. So if I add the 2, 4 from carbon and 4 from the hydrogens, I get a total of 8 electrons. Now this number is super important. I have to use 8 electrons in this structure. If I use more or less, I've automatically done it right. I have 8 valence electrons. It's the valence electrons that I'm using for the bonding, so I have to use 8. So then the third rule is just to add single bonds. We know they all have to have a single bond. So I just put 1, 2, 3, 4. Now in this simple case, now I'll count up, and I'm just going to use a highlighter to kind of say how I'm counting. So I've used 2, 4, 6, 8 electrons. So looking down here, I've used 8 electrons. So I can't put any more electrons on. So I evaluate what I've done. Each hydrogen has a single bond. So that means each hydrogen sees 2 electrons. Hydrogen is complete with a single bond. Then I look at my carbon, and here's the carbon, and it sees 2, 4, 6, 8. So carbon has its complete octet by sharing with the hydrogens. And this, right there, you have done the Lewis structure. In the first 3 steps, that's all I had to do. I did not have to do more steps because by adding the 8 electrons, I have each of the ones have fit the octet rule. So let's try another one. So the NH3 is ammonia. So I would do the skeletal arrangement. So I put nitrogen here, and I put H, H, H. And I just put them around. You could put them above it or on the side. It's just a skeletal arrangement. I think nitrogen's in the middle. I know it is. And the hydrogens are on the outside. Remember, hydrogen can never be in the middle because it can only have a single bond. So the second step is you add up all the valence electrons. So nitrogen has 5 valence electrons because it's in group 5A. I have 3 hydrogens. Well, each hydrogen has 1 electron, but times 3, and that gives me 3 electrons from the hydrogens. So if I add a 5 and a 3, again I have 8, and that's just a coincidence of the 2 problems I picked. So the third step is you add single bonds to attach the atoms. And while there are rings and things like that in chemistry, for this class we're not going to have rings for our Lewis structures. So I added it, and now if I count, I've used 2, 4, 6 hydrogens. 6 electrons. So if you think I've had 8 electrons, but to draw the single bonds, I've already used 6. So that means I still have 2 electrons remaining. The fourth rule says any electrons you have remaining, use to finish out and complete the octet of the outside atoms. Well, my outside atoms are all hydrogens, and they're happy with single bonds, so I don't put any electrons on them. So what do I do with these last 2 electrons? I go to my central atom, and I put that on my central atom. This completes the octet of my nitrogen. Now nitrogen has 2, 4, 6, and then 8 electrons. So this is a completed Lewis structure. Now, what happens if it has double bonds? How would we know if it was a double bond and not just single bonds? The last 2 examples I did were quite easy with just single bonds. Actually, before I do this double bond, let me do one let's say I want to think of one that has, okay, let's say instead of having hydrogens, I had chlorine on the outside. This is carbon tetrachloride. So let's say I do the skeletal arrangement. Whoops, sorry. And then I add up the electrons, so carbon's in 4, it has 4. The chlorines, I have 4 of them total. Each chlorine has 7, but remember to multiply it by 4 because you got to include all of them. That's 28, right? And then 28 plus 4 is 32. So I have 32 electrons. That's way more than the 8 I've been doing. But I'll do the same thing. Single bonds. 2, 4, 6, 8. So I've used 8 electrons, so if you want to think about it, 32 minus 8, that gives me 26 electrons left. Is that right? No, 24. Sorry. 24 electrons left. And so the next step is to make sure your outer atoms have a complete octet. Well, all of the chlorines, they only have 2, and that was fine for hydrogen. Hydrogen only wants 2, but the chlorine need to have lone pairs to finish off their 8. So if I put their lone pairs, whoops, that looks like 3 over there. So 1, 2, 3, 4, 5, 6. 1, 2. By adding 3 lone pairs around each chlorine, I have completed the octet on the chlorine. Now I have 24 electrons to use. Let's count that I used up the 24. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I used up the 24, and then 26, 28, 30, 32. So this structure is complete. Each element has its 8 electrons around it, and I've used the total 32. So even if you have more, the other examples we had hydrogen, but the extra ones, first you put them on the outside, and then if we had any left over, we'd put them on the inside. So let's think about a double bond. So let's say I have carbon dioxide. So you do your skeletal arrangement. Carbon is going to be in the middle, and you count up your valence electrons. So that's 4, and oxygen, I have 2 of them. Each oxygen group 6A, so it has 6. And you look at your periodic table to tell this. Times 2, that's 12. Whoops. Equals 12. And so I'm going to add 14 plus 12, 4 plus 12, sorry. That's 16. So I have a total of 16 electrons to make what I call everybody happy. That means everybody ate. So let's just start. Some of you may already see. So single bonds. Then with the single bonds, I've used 2. So I have 14 more, right? Because I had 6. No, I've used 4. I've used 2, 4. So I'm going to complete. Got to make this pin thicker to do the lone pairs or it messes up. 2, 4, okay. That gives that oxygen enough. And that gives that oxygen enough. So counting it up, and I'm just going to highlight it, I've used 2, 4, 6, 8, 10, 12, 14, 16. So to use this whole thing, I have used, whoops, I have used 16 electrons. I don't know why it's not. Sorry. I was trying to get this back. Let's use that. There we go. I've used 16 electrons right now. So look here. I can't use any more. I've used 16. So I can't add any more dots. And the reason it's a problem because carbon only has 4 electrons around it. Each bond is worth 2 electrons, so it only has 4. So this is the case where you go to step 4 and you've added and you've completed the octet of the outside ones, but your inside element doesn't have a complete octet. So what you're going to do is you're going to take one of the lone pairs, and it doesn't matter which one you want. I'm just going to take off this guy. Whoops, let me erase it. Oh, let me erase it. Oh, come on. My program's giving me a little bit of trouble. There we go. Let me erase it. And instead of making it a lone pair, you are going to change it into a bond. So I took it off, and I'm going to draw a second bond. Oops. I'm going to draw a second bond. Okay, I still have only used 16 because I just rearranged it, but my carbon still is not happy. It only has 2, 4, 6. So what I'm going to do is take off another double bond. Now, another lone pair. Now I could take off this one, which is what I'm going to do because it ends up being symmetrical, and so things will like the symmetry. I could have taken one off the other side and had a triple bond and a single bond. That would be called a resonance structure. A resonance structure is simply another valid Lewis structure. It doesn't mean they're all equally favorable, but some structures have resonances, which just means there's more than one valid Lewis structure. So Lewis structures take practice, and you can look in the study tools. There's some more examples of Lewis structures. But I'm going to stop this one right now because we're already at 16 minutes.